Ytterbium is a chemical element with symbol Yb and atomic number 70. It is the 14th and penultimate element in the lanthanide series, which is the basis of the relative stability of its +2 oxidation state. However, like the other lanthanides, its most common oxidation state is +3, seen in its oxide, halides and other compounds. In aqueous solution, like compounds of other late lanthanides, soluble ytterbium compounds form complexes with 9 water molecules. Because of its closed shell electron configuration, its density and melting and boiling points differ from those of the other lanthanides. In 1878, the Swiss chemist Jean-Charles Galissard de Marignac separated in the rare earth Ytterbium another independent component, which he called Ytterbium, for Ytterby, the village in Sweden near where he found the new component of Ytterbium. He suspected that Ytterbium was a compound of a new element that he called Ytterbium. In 1907, the new earth Lutetia was separated from Ytterbium, from which the element lutetium was extracted by Georges Urbain, Karl Auer von Welsbach, and Charles James. After some discussion, Marignac's name, Ytterbium, was retained. A relatively pure sample of the metal was obtained only in 1953. At present, ytterbium is mainly used as a dopant of stainless steel or active laser media, and less often as a gamma-ray source. Natural ytterbium is a mixture of 7 stable isotopes, which altogether are present at concentrations of 3 parts per million. This element is mined in China, the United States, Brazil, and India in form of the minerals monazite, exonite, and xenotime. The ytterbium concentration is low, because the element is found among many other rare earth elements. Moreover, it is among the least abundant ones. Once extracted and prepared, ytterbium is somewhat hazardous as an iron skin irritant. The metal is a fire and explosion hazard. Characteristics. Physical properties. Ytterbium is a soft, malleable and ductile chemical element that displays a bright silvery luster when in its pure form. It is a rare earth element, and it is readily attacked and dissolved by the strong mineral acids. It reacts slowly with cold water and it oxidizes slowly in air. Ytterbium has 3 allotropes labeled by the Greek letters alpha, beta and gamma. Their transformation temperatures are -13 degrees Celsius and 795 degrees Celsius. Although the exact transformation temperature depends on the pressure and stress, the beta allotrope exists at room temperature, and it has a face-centered cubic crystal structure. The high-temperature gamma allotrope has a body-centered cubic crystalline structure. The alpha allotrope has a hexagonal crystalline structure and is stable at low temperatures. Normally, the beta allotrope has a metallic electrical conductivity, but it becomes a semiconductor when exposed to a pressure of about 16,000 atmospheres. Its electrical resistivity increases 10 times upon compression to 39,000 atmospheres, but then drops to about 10% of its room temperature resistivity at about 40,000 atmospheres. In contrast with the other rare earth metals, which usually have antiferromagnetic and/or ferromagnetic properties at low temperatures, ytterbium is paramagnetic at temperatures above 1.0 Kelvin. However, the alpha allotrope is diamagnetic, with a melting point of 824 degrees Celsius and a boiling point of 1196 degrees Celsius. Ytterbium has the smallest liquid range of all the metals, contrary to most other lanthanides, which have a close-packed hexagonal lattice. Ytterbium crystallizes in the face-centered cubic structure. As a result, its density is significantly lower than E. e.g., those of the neighboring elements thulium and lutetium. The melting and boiling points of ytterbium are also significantly lower than those of thulium and lutetium. These properties stem from the closed shell electron configuration of ytterbium, which causes only the two 6s electrons to be available for metallic bonding. Chemical properties: ytterbium metal tarnishes slowly in air. Finely dispersed ytterbium readily oxidizes in air and under oxygen. Mixtures of powdered ytterbium with polytetrafluoroethylene or hexachloroethane burn with a luminous emerald green flame. Ytterbium reacts with hydrogen to form various non-stoichiometric hydrides. Ytterbium dissolves slowly in water, but quickly in acids, liberating hydrogen gas. Ytterbium is quite electropositive, and it reacts slowly with cold water and quite quickly with hot water to form ytterbium hydroxide. 2Yb plus 6H2O 2Yb3 plus 3H2. Ytterbium reacts with all the halogens 2Yb plus 3Fu2 ytterbium 3 fluoride 2Yb plus 3Cl2 ytterbium 3 chloride 2Yb plus 3Br2 ytterbium 3 bromide 2Yb plus 3I2 ytterbium 3 iodide. The ytterbium ion absorbs light in the near-infrared range of wavelengths, but not in visible light. So the mineral ytterbium 3 oxide is white in color, and the salts of ytterbium are also colorless. Ytterbium dissolves readily in dilute sulfuric acid to form solutions that contain the colorly Yb ions, which exist as non-hydrate complexes. 2Yb plus 3H2SO4 2 3 plus 3SO2 minus 4 plus 3H2Yb versus Yb. Although usually trivalent, ytterbium readily forms divalent compounds. This behavior is unusual to most lanthanides, which almost exclusively form compounds with an oxidation state of +3. The +2 state has a valence electron configuration of 4f14 because the fully filled F shell gives more stability. The yellow-green ytterbium ion is a very strong reducing agent and decomposes water, releasing hydrogen gas, and thus only the colorless ytterbium ion occurs in aqueous solution. Samarium and thulium also behave this way in the +2 state, but europium is stable in aqueous solution. Ytterbium metal behaves similarly to europium metal and the alkaline earth metals, dissolving in ammonia to form blue electride salts. Isotopes: natural ytterbium is composed of 7 stable isotopes: 168 Yb, 170 Yb, 171 Yb, 172 Yb, 173 Yb, 174 Yb, and 176 Yb, with 174 Yb being the most abundant isotope, at 31.8% of the natural abundance. 27 radioisotopes have been observed, with the most stable ones being 169 Yb with a half-life of 32.0 days, 175 Yb with a half-life of 4.18 days, and 166 Yb with a half-life of 56.7 hours. All of its remaining radioactive isotopes have half-lives that are less than 2 hours, and most of these have half-lives are less than 20 minutes. Ytterbium also has 12 metastates, with the most stable being 169 MyB. The isotopes of ytterbium range in atomic weight from 147.9674 atomic mass unit for 148 Yb to 180.9562 U for 181 Yb. The primary decay mode of ytterbium isotopes lighter than the most abundant stable isotope, 174 Yb, is electron capture, and the primary decay mode for those heavier than 174 174Yb is beta decay. The primary decay products of ytterbium isotopes lighter than 174Yb are thulium isotopes, and the primary decay products of ytterbium isotopes with heavier than 174Yb are lutetium isotopes. Occurrence: ytterbium is found with other rare earth elements in several rare minerals. It is most often recovered commercially from monazite sand. The element is also found in exonite and xenotime. The main mining areas are China, the United States, Brazil, India, Sri Lanka, and Australia, and reserves of ytterbium are estimated as 1 million tons. Ytterbium is normally difficult to separate from other rare earths, but ion exchange and solvent extraction techniques developed in the mid to late 20th century have simplified separation. Known compounds of ytterbium are rare and have not yet been well characterized. The abundance of ytterbium in the Earth's crust is about 3 mg per kilogram. As an even-numbered lanthanide, in accordance with the Oddo-Harkins rule, ytterbium is significantly more abundant than its immediate neighbors, thulium and lutetium, which occur in the same concentrate at levels of about 0.5% each. The world production of ytterbium is only about 50 tons per year, reflecting the fact that ytterbium has few commercial applications. Microscopic traces of ytterbium are used as a dopant in the YB-YAG laser, a solid-state laser in which ytterbium is the element that undergoes stimulated emission of electromagnetic radiation production. It is somewhat difficult to separate ytterbium from other lanthanides due to its similar properties. As a result, the process is somewhat long. First, minerals such as monazite and xenotime are dissolved into various acids, such as sulfuric acid. Ytterbium can then be separated from other lanthanides by ion exchange, as can other lanthanides. The solution is then applied to a resin, which different lanthanides bond to in different matters. This is then dissolved using complexing agents, and due to the different types of bonding exhibited by the different lanthanides, it is possible to isolate the compounds. Ytterbium is separated from other rare earths either by ion exchange or by reduction with sodium amalgam. In the latter method, a buffered acidic solution of trivalent rare earths is treated with molten sodium-mercury alloy, which reduces and dissolves Yb3+. The alloy is treated with hydrochloric acid. The metal is extracted from the solution as oxalate and converted to oxide by heating. The oxide is reduced to metal by heating with lanthanum, aluminium, cerium, or zirconium in high vacuum. The metal is purified by sublimation and collected over a condensed plate. Compounds. The chemical behavior of ytterbium is similar to that of the rest of the lanthanides. Most ytterbium compounds are found in the +3 oxidation state, and its salts in this oxidation state are nearly colorless. Like europium, samarium, and thulium, the trifhalides of ytterbium can be reduced to the difhalides by hydrogen, zinc dust, or by the addition of metallic ytterbium. The +2 oxidation state only occurs in solid compounds and reacts in some ways similarly to the alkaline earth metal compounds. For example, ytterbium oxide shows the same structure as calcium oxide. Halides. Ytterbium forms both difhalides and trifhalides with the halogens fluorine, chlorine, bromine, and iodine. The difhalides are susceptible to oxidation to the trifhalides at room temperature and disproportionate to the trifhalides and metallic ytterbium at high temperature. 3Ybx22Ybx3+Yb. Some ytterbium halides are used as reagents in organic synthesis. For example, ytterbium chloride is a Lewis acid and can be used as a catalyst in the aldol and Diels-Alder reactions. Ytterbium iodide may be used, like samarium iodide, as a reducing agent for coupling reactions. Ytterbium fluoride is used as an inert and non-toxic tooth filling as it continuously releases fluoride ions, which are good for dental health, and is also a good X-ray contrast agent. Oxides. Ytterbium reacts with oxygen to form ytterbium oxide, which crystallizes in the rare earth C-type sesquioxide structure, which is related to the fluoride structure with 1/4 of the anions removed, leading to ytterbium atoms in two different 6-coordinate environments. Ytterbium oxide can be reduced to ytterbium oxide with elemental ytterbium, which crystallizes in the same structure as sodium chloride. History. Ytterbium was discovered by the Swiss chemist Jean-Charles Galissard de Marignac in the year 1878. While examining samples of gadolinite, Marignac found a new component in the earth then known as erbia, and he named it Ytterbia for Ytterby, the Swedish village near where he found the new component of erbium. Marignac suspected that ytterbia was a compound of a new element that he called ytterbium. In 1907, the French chemist Georges Urbain separated Marignac's ytterbia into two components, neo-ytterbia and lutetia. Neo-ytterbia would later become known as the element ytterbium, and lutetia would later be known as the element lutetium. The Austrian chemist Carl von Welsbach independently isolated these elements from ytterbia at about the same time, but he called them aldebaranium and cassiopium. The American chemist Charles James also independently isolated these elements at about the same time. Urbain and Welsbach accused each other of publishing results based on the other party. The Commission on Atomic Mass, consisting of Frank Wigglesworth Clark, Wilhelm Ostwald, and Georges Urbain, which was then responsible for the attribution of new element names, settled the dispute in 1909 by granting priority to Urbain and adopting his names as official ones, based on the fact that the separation of lutetium from Marignac's ytterbium was first described by Urbain. After Urbain's names were recognized, neo-ytterbium was reverted to ytterbium. The chemical and physical properties of ytterbium could not be determined with any precision until 1953, when the first nearly pure ytterbium metal was produced by using ion exchange processes. The price of ytterbium was relatively stable between 1953 and 1998 at about $1,000 per kilogram. Applications. Source of gamma rays. The 169 Yb isotope, which is created along with the short-lived 175 Yb isotope by neutron activation during the irradiation of ytterbium in nuclear reactors, has been used as irradiation source in portable X-ray machines. Like X-rays, the gamma rays emitted by the source pass through soft tissues of the body, but are blocked by bones and other dense materials. Thus, small 169 Yb samples act like tiny X-ray machines useful for radiography of small objects. Experiments show that radiographs taken with a 169 Yb source are roughly equivalent to those taken with X-rays having energies between 250 and 350 keV. 169 Yb is also used in nuclear medicine. World's most stable atomic clock. Ytterbium clocks hold the record for stability, with ticks stable to within less than 2 parts in 1 quintillion. The clocks developed at the National Institute of Standards and Technology rely on about 10,000 rare earth atoms cooled to 10 microkelvin and trapped in an optical lattice, a series of pancake-shaped wells made of laserlight. Another laser that ticks 518 trillion times per second provokes a transition between two energy levels in the atoms. The large number of atoms is key to the clock's high stability. doping of stainless steel. Ytterbium can also be used as a dopant to help improve the grain refinement, strength, and other mechanical properties of stainless steel. Some ytterbium alloys have rarely been used in dentistry. Ytterbium as dopant of active media. The ytterbium +3 ion is used as a doping material in active laser media, specifically in solid-state lasers and double-clad fiber lasers. Ytterbium lasers are highly efficient, have long lifetimes and can generate short pulses. Ytterbium can also easily be incorporated into the material used to make the laser. Ytterbium lasers commonly radiate in the 1.06 to 1.12 micrometers band, being optically pumped at wavelength 900 nanometers to 1 micrometer, dependently on the host and application. The small quantum defect makes ytterbium a prospective dopant for efficient lasers and power scaling. The kinetic of excitations in ytterbium-doped materials is simple and can be described within the concept of effective cross-sections. For most ytterbium-doped laser materials, the Macumber relation holds, although the application to the ytterbium-doped composite materials was under discussion. Usually, low concentrations of ytterbium are used. At high concentrations, the ytterbium-doped materials show photodarkening or even a switch to broadband emission instead of efficient laser action. This effect may be related with not only overheating, but also with conditions of charge compensation at high concentrations of ytterbium ions. Much progress has been made in the power scaling lasers and amplifiers produced with ytterbium-doped optical fibers. Power levels have increased from the 1 kW regimes due to the advancements in components as well as the YB-doped fibers themselves. Fabrication of low-NA, large mode area fibers enable achievement of near-perfect beam qualities at power levels of 1.5 kW to greater than 2 kW × 1064 nanometers in a broadband configuration. Ytterbium-doped LMA fibers also have the advantages of a larger mode field diameter, which negates the impacts of nonlinear effects such as stimulated Brillouin scattering and stimulated Raman scattering, which limit the achievement of higher power levels, and provides a distinct advantage over single-mode ytterbium-doped fibers. In order to achieve even higher power levels in ytterbium-based fiber systems, all factors of the fiber must be considered. These can only be achieved via optimization of all the ytterbium fiber parameters, ranging from the core background losses to the geometrical properties, in order to reduce the splice losses within the cavity. Power scaling also requires optimization of matching passive fibers within the optical cavity. The optimization of the ytterbium-doped glass itself through host glass modification of various dopants also plays a large part in reducing the background loss of the glass. Improvements in slope efficiency of the fiber and improved photodarkening performance, all of which contribute to increased power levels in 1 micrometer systems. Others, ytterbium metal increases its electrical resistivity when subjected to high stresses. This property is used in stress gauges to monitor ground deformations from earthquakes and explosions. Visible light waves oscillate faster than microwaves, and therefore optical clocks can be more precise than cesium atomic clocks. The Physikalische Technische Bundesanstalt is working on several such optical clocks. The model with one single ytterbium ion caught in an ion trap is highly accurate. The optical clock based on it is exact to 17 digits after the decimal point. A pair of experimental atomic clocks based on ytterbium atoms at the National Institute of Standards and Technology has set a new record for stability. NIST physicists report in the August 22, 2013 2013 issue of Science expressed that the ytterbium clock sticks are stable to within less than 2 parts in 1 quintillion, roughly 10 times better than the previous best published results for other atomic clocks. The clocks would be accurate within a second for a period comparable to the age of the universe. Currently, ytterbium is being investigated as a possible replacement for magnesium in high-density pyrotechnic payloads for kinematic infrared decoy flares, as ytterbium oxide has a significantly higher emissivity in the infrared range than magnesium oxide. A higher radiant intensity is obtained with ytterbium-based payloads in comparison to those commonly based on magnesium, Teflon, Viton. Precautions. Although ytterbium is fairly stable chemically, it is stored in airtight containers and in an inert atmosphere such as a nitrogen-filled dry box to protect the metal from air and moisture. All compounds of ytterbium are treated as highly toxic, although initial studies appear to indicate that the danger is minimal. Ytterbium compounds are, however, known to cause irritation to the human skin and eyes, and some might be teratogenic. Metallic ytterbium dust can spontaneously combust, and the resulting fumes are hazardous. Ytterbium fires cannot be extinguished using water, and only dry chemical Class D fire extinguishers can extinguish the fires.